Hi, welcome to today's video where we'll be talking about the challenges for hydrogen power. What is hydrogen power? Hydrogen is often hailed as a clean energy solution. It holds immense potential in addressing environmental concerns and is transitioning towards a sustainable energy system. Hydrogen has surged due to its potential across multiple applications, some including energy storage, which stores energy from solar and wind, heating and residential application, which includes utilizing hydrogen for heating in homes and businesses, offering a clean alternative to natural gas. A thermodynamics analysis of hydrogen power become essential while searching for a sustainable energy source. A basic foundation for assessing hydrogen generation and use is provided by thermodynamics, the study of energy transition and their efficiency. The efficiency of hydrogen power, often measured in terms of work output over time and energy efficiency. Efficiency is a crucial factor in hydrogen manufacturing processes like steam reforming and electrolysis. The efficiency of these energy-intensive processes must be assessed in order to comprehend the overall sustainability of hydrogen as an energy source. Additionally, assessing how simple it is to operate hydrogen power system helps to maximize their performance and guarantee their integration into current energy infrastructures.
Why hydrogen? Despite what my partner has just stated to you, hydrogen has been commonly overlooked as a fuel source to power transportation. That being said, a major shift happened that in turn changed this. The change from traditional gasoline to hydrogen is based on a goal for a significant reduction in carbon emissions. Lots of companies are looking into eco-friendly cars and vehicle production processes for the near future. And these companies are leading towards hydrogen power. But again, why hydrogen? To start, hydrogen has the highest energy per mass of any fuel at roughly 120 megajoules per kilogram. This means hydrogen obliterates gasoline and diesel at 44 and 43 respectively. Its higher energy per mass translates into longer distances for cars and or reduction of the amount of fuel needed. But its low volumetric energy density as gas results in a lower energy per unit volume. Its specific volume capacity is 3 times 10 to the negative second kilograms of hydrogen per liter, or 1 kilowatt hour over a liter. This representing the net useful energy mass system volume. Having a low volumetric energy density results in high permeability, making it hard to store in most materials as the hydrogen molecules are able to pass through the materials of most containers. This is why scientists have opted to using high pressure tanks to contain hydrogen. To store hydrogen in an high pressure tank of 5,000 to 10,000 psi or psia is required. At 1 atmospheric pressure, which is roughly 14.7 psia, right? That would be right here. That's between 13.5 and 23.7, which coincides with the temperatures in Celsius, negative 253 and negative 251, which would leave our temperature roughly negative 252 Celsius. The biggest problem with these high pressure tanks is the size and practicality. A standard steel 5,000 psi tank has a height of 52.5 inches and a weight of 170 pounds when empty. This is currently being researched and developed with scientists testing thick plastic lining, carbon fiber materials, and aluminum to produce a higher efficient car for weight and charging. Refueling. Another supposed selling point of hydrogen fuel cells is that it'll have a fast refueling time. Um, so fast that it'll be comparable to the refueling time of gasoline. This, however, presents many problems. The fast refueling rate would rise temperatures in the tanks due to the compression effect. It's modeled as such. It would leave two possible problems. The gas tank liner would heat up, causing an unstable structural integrity of the tank, and or the high temperature reduces the hydrogen density of the tank, which reduces the final mass delivery, as you can see in the diagram I've provided for you. Arguably, one of the biggest flaws in hydrogen power is the fact that it isn't naturally available. Hydrogen is the most abundant element on Earth, but pure hydrogen is rare. So, in order to use it to fuel and power our vehicles, we need to mass manufacture it. To create pure hydrogen, we use electricity to split water molecules and remove hydrogen from oxygen, taking the H out of H2O. This process can emit 1 kilogram or less of carbon dioxide per kilogram of hydrogen produced. Yeah. That being said, it would still emit less than a typical car that runs on gasoline fuel, which has 8.8 kilograms of CO2 per gallon. A typical diesel car also would have high amounts at 10.2 kilograms of CO2 per gallon. This in turn would pale in comparison with the zero carbon emissions per gallon that hydrogen would produce because it would come out as a vapor. Hydrogen could be the fuel of the future, but it does have its challenges.
Innovations in hydrogen production. Well, over the years, electrolysis, particularly using renewable energy sources like solar and wind, has gained attention. This process is known as green hydrogen production, and it essentially splits water into hydrogen and oxygen using electricity. Recent advances in catalyst materials have enhanced thermodynamics efficiency by optimizing active sites and using novel materials such as single atom catalysts. These all together aim to improve catalytic processes and reduce energy consumption. We're going to talk about two key thermodynamic considerations in the next generation electrolysis technologies: the Gibbs free energy and cell voltage, and also the overpotential. The Gibbs free energy change of the electrolysis reaction determines the feasibility of the process. The other consideration would be overpotential, as the voltage required to drive the reaction at a desired rate compared to the thermodynamically predicted voltage would be greater. We are going to talk about the collaborative efforts in the scientific community. International research partnerships play a crucial role in addressing thermodynamics challenges in various fields, including energy, materials science, and environmental science. Examples include hydrogen production and storage. It is also being targeted by different countries as they are trying to find a way to produce and store it. Renewable energy systems is also internationally collaborated between different countries, with their main focus being to solve problems with solar and wind power. Lastly, high temperature material research has an ongoing partnership with several universities of different countries, and they are working on researching materials for high temperature applications, including solid oxide fuel cells and high temperature electrolysis.
The potential of hydrogen power as a flexible and clean energy source is enormous. However, A number of obstacles prevent its effective use and broad adoption, such as production costs, storage and transportation, safety concern, policy and regulation, technological innovation. In conclusion, even though hydrogen power has a lot of promise as a clean and sustainable energy source, overcoming these obstacles would need teamwork and the creation of new infrastructure, supportive laws, and public awareness. Campaigns in order to fully reap the benefits of hydrogen power when these obstacles are overcome. Hydrogen will be able to take center stage in the world's energy transition.